his paper on, you may recognize again, the robots here and the flexible sensor. I'm not going to say more. I think Frontis is basically ready to tell us the details.
Yeah, thank you. Thank you very much for coming here. It's been a very interesting event so far, and we will try to present you briefly our demonstration. Okay, as you already know, one of the main goals of this workshop is to try to discuss and come up with a roadmap to intelligent structures. So towards this end, in our presentation, we will try and make an effort to present how we can transform an unintelligent dummy structure to an intelligent one. So, the main motivation from this work originates from the use of biological systems. We all know that the human body is a great example of how we can transform, of a biological system which can sense the external environment and make some optimal decisions in real time. Therefore, our goal is also being inspired by the human body to design and integrate an intelligent structure which will be able to sense the environment, process this information, and make some optimal decision during its operation. The technology that we believe that may enable this transformation is based on the use of stretchable sensor networks, and which were also presented in the keynote speech of Professor Chang. So the main advantages that we find in this technology are, first of all, that the stretchable sensor networks can cover large areas of the structure. They can be integrated with micro and nano sensors during the manufacturing. And also we can have direct integration with electronics, and also we can embed they can be embedded in composites during manufacturing. Also, another very important advantage of this technology is that stretchable sensor networks, because of their small size, are non-intrusive and have no parasitic effects on the structure. Actually, we can consider them as being micro devices that can be applied to micro-scale applications. Okay, having designed a stretchable sensor network, the next step is to try to protect the network from the external environment and allow its integration in complex geometries. So, for this reason, we try to come up with a skin based, again inspired from the human body, which is a silicon-based thin skin with embedded sensor network. The thickness of the skin is about 0.3 millimeters, whereas the sensors are embedded 0.1 millimeter from the surface of the skin. So, using the skin, we can integrate flexible PCBs and electronics at the same time, and also we can implement complex skin geometries. We can see a small video of the manufacturing process of the skin. First, we have to stretch the network, and afterwards we will try to embed the network inside the silicon. So, the goal of this demonstration is to integrate all these technologies to an intelligent robotic arm. The main tasks of the robotic arm that we're going to see in the following is, first of all, that it is a pick and drop mechanism that is capable of picking an object from its initial location and dropping it to a desired target location. Also, the robot is capable of measuring the target object temperature and assess whether it is safe or not to grasp. And finally, it is capable of identifying and avoiding hot temperature areas and obstacles. As you can see, the complete loop of the robotic arm system is, first of all, we have the sensing part, then we have the diagnostic part, which is related to some signal processing techniques for the data conversation and normalization, based on which we achieve the state awareness. And finally, we have the control, which is achieved in real time, and it has been designed in collaboration with Professor Marco Pavone's group in Aeronautics and Astronautics here at Stanford. So I think it's time that we can see the real application of the robotic
So it's pretty small, if I show you here. And this one is stretchable. It's around 10 times. Well, sorry. So with our process, we have embedded the sensor in silicone to make skin. We can make really complex geometry, seems like this one. We can put it on a bowl, for example. This one seems like what you have on the robotic arm. Okay. Or we can make flat skin for developable shape. We can make in the same time really large area if we want, or bigger than this one. And we can put it, for example, on a UAV wing. It's stretchable, and we can fold it, handle it without problem. So now it's time to show.
Okay, so the robotic arm on the right is a commercial robotic arm, which costs about $200. And actually, we have it's just a robotic arm without any integration, without any intelligence. It's off-the-shelf robotic arm. So you can see that even if we have an object, if we don't have an object, the robotic arm is going to make the full motion, the full trajectory, and will try to pick the object and drop it on a small cab. On the other hand, we have the smart robotic arm, which is capable actually of determining whether we have an object. So if we remove the object, the robotic arm is able to sense it and will make a decision to go back to its initial location. Okay. So the pressure sensor is sensing no object, and it goes back to its initial location. In the next round, it will sense that there is an object to grasp. We had a bad power supply, it seems like, due to this, to all the electronics. And then we will introduce a hot obstacle, and you see, it may reset to its initial position if it has not grabbed the object, and also it can calculate online an alternative trajectory path. Okay, I think we don't have much time. We're sorry for this, I mean, the electronics and sometimes the data connections, we have this issue, so yeah. Thank you very much.